All right.
Well, I'm never ready to go to work, but I'll try. Okay, let's put it that way.
Okay, so our next speaker is Mizan R from Eastern Connecticut State University, who will count clean triangles, I guess. Please.
Yes. I'm going to talk about some recent work that I did with my brother, who is now in Bangladesh. And in the course of doing this work on counting clean triangles, we had to come up with a variant on the Euler phi function. I'll talk about all of this. But the first thing that I would like to do is to thank the organizers for once again organizing this wonderful conference. In particular, our guru, Mel the Man Nathanson. Do you want guru or do you want ustad? You have your choice. Okay. All right, Mel's not responding. Okay, so in my talk, there's going to be two main points. In the first, I'm going to begin by describing Scott's inequality for convex lattice polygons in 2 dimensions. And this is what, when we were studying it, this is what motivated us to go on to count clean triangles. The proof of Scott's inequality is really provided the initial motivation. All right, so let me start off by what I think is a truly awesome example of a lattice triangle. So the awesome example is the following. It's the 3 by 3 right angle lattice triangle. And this is truly an awesome triangle. Now you may be wondering why, and let me explain in just a few minutes. But what we notice is that there are 9 lattice points on the boundary and 1 in the interior. Okay. And if you do a calculation on AE, you take the number of lattice points in the interior, which is 1, you multiply it by 2, and you add 7, voila, you get 9, which is the number of lattice points in the boundary. And this is truly a remarkable equality. Again, you're probably wondering what's going on. Has the speaker completely lost his mind? And that may well be the case. But what we have is this beautiful inequality of Scott from 1976. So let's say we have a convex lattice polygon in 2 dimensions, and it has an interior lattice point. Okay, so you have to insist that there's at least 1 lattice point inside. Then twice the number of interior lattice points plus 7 is an upper bound for the number of boundary lattice points. Okay, this is all, and in fact, our example AE is a kind of extreme case. It's only when you have that you get equality. Otherwise, it's always a strict inequality. So that's why that's a really lovely triangle, in my opinion. And what I'd like to do is I'd like to sketch the proof of Scott's inequality for lattice triangles. Okay. Everything, by the way, I should have mentioned at the beginning that everything is quite elementary. I'm not going to be doing any, I mean, this is, I like to view it as very lowbrow number theory, unlike nearly all of the other talks in this conference. I mean, so let's sketch a proof of Scott's. So what starts of the proof is that you want to work with unimodular maps. So what are these maps? Well, basically, they're a map from R2 into R2, where you multiply by your matrix in GL2Z, and you have a translation. Okay, so M is a 2 by 2 matrix, integer entries, determined plus or minus 1, and any translation you have must be a lattice point. Okay, so this is the basic tool we need. And so what we do is we take whatever lattice triangle we have, and we choose appropriate unimodular maps. And when you do so, when you do it correctly, your lattice triangle gets transformed to something like this, where one of the vertices is at the origin, the second vertex is on the x-axis, and the third vertex is in the first quadrant. One thing I should point out is that M it can be equal to B or greater than B. The way I've drawn it, M seems to be less than B, but we really don't insist on that. But there's one condition we want for the base. We want that the number of lattice points on the base is never less than the number of lattice points on either of the other two sides. Okay, so, and that is taken care of by this little inequality on the GCD. Okay, so we transform our lattice triangle using unimodular maps into something, into a triangle that looks like this. And then the second thing we use is Pick's theorem for on lattice polygons. So you write this expression 2i minus b like this. Remember that we're looking at the expression, we're wanting to show that 2i plus 7 is greater or equal to b. So we take 2i minus b, we use Pick's theorem, we write it this way, and then with some algebraic manipulation, we get this inequality. And then by doing a few simple checks, we show that this product is always non-negative. And that's how you prove it for lattice triangles. The general case for Scott's inequality is along the same lines. There are some subtleties, but it's basically along the same lines. Okay. I should mention that Scott's inequality has been improved to the following. If V represents the number of vertices of the polygon, then, and you have the same hypotheses, then the sum of the vertices plus the number of boundary points is bounded above by 2i plus 10. This was conjectured by Coleman in '78, and the first proof that was written down was in 2005. I'm sorry, I'm unable to pronounce the names of the people who wrote down the proof. Okay. All right, so that is basic outline of how Scott's inequality was proved. And we were very taken by the unimodular maps that were used in Scott's theorem. And we asked ourselves, what else can we do with them? And one answer was to see what would happen if we applied them to clean triangles. So what's a clean triangle? It's a lattice triangle, so a triangle all of whose vertices are lattice points. And it's called clean if there are no lattice points on the boundary that are not vertices. So no boundary, no non-vertex boundary lattice points. Okay, and if you take a piece of graph paper and you play around, you can see that there's, you can draw all kinds of clean triangles. So if you choose the appropriate unimodular maps, this is what a clean triangle can be transformed into. Okay, so one vertex is at the origin, the other vertex is at 1, 0, and the third vertex is at is in the first quadrant. Because you can't have any boundary points, lattice boundary points between these two vertices, either on this side or on this side, you have this condition on the GCD. The other thing that I would like to mention is that the height has to be odd. I mean, many ways to see that, but once you have this condition, you see that if H is even, then either this or this will be equal to, will be greater or equal to 2. So, or in other words, what one realizes is that any clean triangle cannot have integer area. Okay. So after looking at these triangles, we came up with the following content question. So let me first tell you what we mean by when we say that two lattice polygons are equivalent. Basically, it means that there's a unimodular map which maps one into another. And so what we see is that if we fix an odd H under this property of lattice equivalence, the number of clean triangles of area H over 2 is less or equal to the cardinality of the set. So this looks very much like the set that arises when you define the Euler-Phi function, except that you have this additional condition on the GCD. You just don't have GCD of A and H equals 1. You also are looking at A minus 1. So the question that we asked ourselves, okay, we have this inequality, we have this upper bound on the number of clean triangles. Can we get an exact count? Okay, so we have to set up some machinery. And so we call this set that we came up with IP of n, and we decided to call it the cardinality, the imitation phi of n, or imph. It was a choice between either going with imitation phi or fake phi, and we decided to go with imitation phi, but maybe the audience would disagree with me. Anyway, imph is very much like the phi function. It's a multiplicative, and you have this formula for the prime power. So the only difference from the Euler-Phi function is you have a 2 instead of 1. And this function has actually appeared in, we've located a paper in graph theory that uses this function, and it is in the OEIS. But I think our name is far more poetic and mellifluous. Okay. So now let's look at when two clean triangles, same height, are equivalent. So you play with the unimodular maps. So the thing is that basically, we fixed H, these two vertices are fixed, and we want to see when these two lattice triangles are equivalent. And when you do a little bit of work, you just check various unimodular maps, various possibilities. You get that these two lattice triangles are equivalent if and only if this x coordinate belongs to this set. And so once you look at this set, what you realize is that you've got a group action on IP of H. So basically, we have S3 acting on IP of H. You define these 6 maps based on these elements. And under composition, they form the symmetric group S3. And so this set that I wrote down is simply the group orbit S3. So now we have a group action on a set, and it's only natural to invoke Burnside. But let me first restate the counting question. So by this calligraphic of n, we're looking at the number of inequivalent clean triangles of area n over 2. And we saw that for even numbers, this is equal to 0. And so what we want, our goal is to find a formula for T of n when n is odd. So to do this, we use Burnside. We have a group action. And Burnside's lemma just tells us that when n is odd, T of n is simply the sum of the fixed values of the GIs divided by 6, which is the cardinality of S3. So to get our formula, we just have to work out what these numbers are for each odd n. It's very easy when for the first one, G1, because that's the identity. And that's simply imph of n. For the other maps, G2 to G6, we have to play with congruences. But if you're, basically you just have to play with Hansel's lemma and it all falls out quite nicely. So here's our result for the counting formula. So there's 3 cases. Omega of n is the number of distinct prime divisors of n. And so this is what we get. Okay. So this is our formula, and it all worked out quite beautifully. All right. I just want to mention one thing about the orbits. Most of the orbits of the action of S3 are 6, but there's always an orbit of size 3, which is this one. And you can get orbits of size 2 provided this one has this congruence has a solution. Okay. The other thing that we did was we decided to try and work out the average order of T of n, and that basically boils around to working out the average order of imph of n. And so when we did that, and it came out very nicely, and basically this is the average order of imph of n. And the nice thing is that this infinite product actually has appeared in the literature before. If you include the contribution of 2, and we've got it greater than 3 because there are no imph of any power of 2 is 0, or any even is 0. But this infinite product is actually slightly modified, is what is called the Feller-Tornier constant. So this was a nice little thing that we learned along the way. By the way, I should mention one thing is that even though I've given my brother and I the credit for proving that theorem, it's very possible that in some of Bruce Resnick's work on clean simplices, that this basic theorem is lurking in there. I mean, I haven't been able to locate it, but Bruce has done so much work on it. I wouldn't be surprised if he has it's squirreled somewhere in there. Okay. And so that's all I have to say, except that I want to give the audience a charge. So here's my charge to the audience. There are some wonderful words in the English language, such as oomph, oops, oof, O for oafs. And I would like you all to find arithmetical functions or classes of arithmetical functions which fit these names. I think this is something I'm hoping will happen in the not too distant future. Thank you so much for listening to me.
Thank you very much, Mizan. Are there any questions for the speaker? If not, then I thank Mizan again for his very interesting talk.